Um, okay, everybody. So, uh, the last topic we covered on the compositions, quality checking the compositions was uh, discussing the theoretical side of how we can do the quality check of the lab measured compositions for the flash oils, and we discussed like for doing the quality check, you need special tools. For example, you need the gamma distribution model, and the gamma distribution model that you are using, it should be tuned to multiple samples that are representative of your field. And if you have a perfect composition, like a perfectly measured composition from gas chromatograph without any errors, gamma distribution or tuned gamma distribution model should be able to predict that compositions very accurately. So that's something we discussed yesterday, and we also discussed not yesterday, but like in the last topic of this in the our previous topic of using the compositions, um, and what we also discussed, like what are the different types of errors that are normally found in the gas chromatography, baseline shift and internal standard, and we also discussed what is the consequence if you have, for example, internal standard error, what will be affected by the internal standard error, and how we can go about correcting it. Okay, so now in this lesson, we will try to use the knowledge that we got from the previous lesson, and try to see if we can implement that knowledge to quality check the compositional data, quality check the compositional data. And so yeah, and for that purpose, we have an Excel spreadsheet where we have programmed the gamma distribution model. So we will be using that Excel spreadsheet, and you can use that Excel spreadsheet for with any gamma distribution model you have, but you need to know all the parameters, the tune parameters of the gamma distribution model, and that's something we will discuss in detail in this lesson, how we can use that Excel spreadsheet, and how you can identify the different types of error, and also try to correct the lab reported compositions. Okay, so before we go and see what how the Excel sheet looks like, what's important to understand here is that when you get a composition from the lab data, okay, you have a flashed oil composition, and yeah, one more thing just to emphasize, because that's something we discussed in the last lesson, and we are doing it now, is that when we are talking about the QCing the composition, there are two aspects. One is doing the QC of the calculated lab calculated data, and that's something we have emphasized a lot in this lesson, that uh, we talked about the recombination QC, the mass to mole conversion QC. That's all relevant to do the QC of the lab calculated data. But now what we are discussing is how to do quality check the measured data, which are flashed oil compositions. So once you get the measurement of the flash oil composition for the lab data, you have like 10 samples, 15 samples, or like 100 samples. You don't know which sample has what problem. Okay, which sample has only an internal standard problem, which sample has only baseline shift problem, which sample has both problems. And sometimes lab may use internal standard for measuring the composition. Sometimes they don't use the lab, and they don't use internal standard. So that's always a good practice, that if you are using some lab for doing compositional measurement, you should always ask the lab if they have used internal standard. And sometimes PVT labs, they give the chromatogram, the signal, the raw signal they get from the gas chromatography. They put the picture of that in the PVT report, and there they mention the internal standard usually. But still, it's a good practice always that you should ask the lab what internal standard is used, and whether they have used any internal standard in the gas chromatography measurement. And even if the lab has used internal standard, it doesn't mean that there should not be an internal standard error, because using internal standard error, using internal standard in PVT lab requires very diligent handling. And even if a lab has used internal standard, there might be very small internal standard error. There might be some small error in the gas chromatography uh, due to uh, due to the internal standard uh, mishandling, what you can say, in the PVT lab, because it's all these measurements are prone to error, because yeah, we are not being humans, we are not perfect. So and also, like all the instruments that we use, they have uh, some yeah, you can expect some errors from those measurements, from those instruments. So yeah. So what we were talking about is that when you get a composition, you don't know whether the given composition has what type of error. Okay, so the first process that we should be doing, like when we get a composition, is first, like, we should try to identify whether the error that's there, is it a baseline shift error or an internal standard error, or both. Okay, so what we start with is we start with assuming that both errors are present, and we start our process with this assumption, and the process will tell us whether it's only an internal standard problem or a baseline shift problem, or both. Okay, so if we make this assumption, with this assumption, the workflow is that we perform this gamma distribution modeling with CX. And if you remember that the CX is the first component from which, for example, the baseline shift problem starts, right? Or in general, you can say the CX is the first carbon number from which you have error in the gas chromatography. Okay, so what we will be doing is that we will be varying the CX carbon number, like the CX value from C16. Generally, this is something we have discussed also, that uh, this X value can vary from, like, for example, generally from 15. It can be somewhere between 15 and 25. So what we will be doing is that we will be varying this carbon number CX from C16 to the heaviest fraction. Yeah, to the heaviest fraction, which is in our case is C26 plus in the lab data we have. And we will be performing the gamma modeling of the lab reported data. And what do we mean by gamma modeling? That's something we have discussed, that we will try to uh, match the relative areas from the lab reported data. Okay, and how do we define the ARI value? Okay, so ARI is equal to the AI divided by sum of all the areas starting from 1 to x minus 1. Okay, so that will be an exercise that we will do, and we should be doing, start and changing this x value here. So x start from 16, and it will go to, for example, here in this exercise, the 26 plus. So for each x value, we will be doing this gamma distribution model, and like trying to fit the relative areas from the lab data. And we have what we have also discussed, that ARI, the relative area, you can represent it as the ratio of the areas, or you can also represent it as the ratio of mass amounts that are reported in the lab. because both are kind of proportional. So you can also write it like this. Okay, and make it a bit clear. Okay, so yeah, so that's what we will be doing. And what we have also discussed before, that when we will try to match these lab relative areas, um, we will be regressing on this mn plus molecular weight. So that in our case is, for example, the C7 plus molecular weight. So we will be regressing on the C7 plus molecular weight and we'll be calculating a new total mass. Okay. And yeah, so we will see in the Excel file how the new total mass is calculated, but that's something we discussed also before, that the new calculated mass. So that will be the calculated mass, which will be the mx minus, which is, maybe we can just write it like sum of all masses from I equals to 1 to x minus 1. Okay, so that's and then we have sum of mi values I equals to x to n plus value. Okay, so n plus is here, and so this is what we call mx plus. So in the Excel spreadsheet, what you will find out that this is, so this should be the same as the lab, like, because we know that all these mass fractions, all these mass values or area values, and until x minus 1, those should be accurate. So that should be the same as the lab value. Okay, and then this should be a new calculated value. Okay, and that will give us a new calculated mass. Okay, yeah, and we have also discussed that this new total calculated mass, if you have only baseline shift problem, then what gamma model is going to give you, that the new total calculated mass will be equal to the lab reported total mass, because we know that the error in the total mass or total area comes from the internal standard. Okay, so if you have only baseline shift problem in your gas chromatography, then the gamma model should be able to give you the exact total mass, the calculated mass, which the lab is reporting. Okay, okay, so so that's what we call the error identification process, and that's something we should be doing before we um, yeah, because we don't know what kind of error is there in the given compositional data. So we have to follow some kind of workflow to identify which sample has what kind of problem. And once we know the problem, then we can make a correct for that problem and correct the compositional data. Okay, so now before we discuss further in this presentation, we can jump to the Excel sheet that we have, which we will be using for this exercise, for this topic. And this is the Excel sheet, like gamma model compositions QC. We go to data sheet. Okay, so here we have four samples, sample 1, 2, 3, and 4. We have components, and then we have mass percentages, and that's something we have also discussed before, that for flashed oils, the compositions that are measured in the lab are mass fractions, so we should always be using those numbers for QCing purposes. And So this first sample, this is actually the flashed oil from our gas condensate PVT report. Okay, so where do we have that flashed oil? Just we can go to the PVT report quickly and see. Um, okay, so when we are on the compositions sheet, and then if you go on the left, you see we have a separator oil, and then separator oil has flashed oil and flash gas. So this is the composition that we have there in the Excel spreadsheet for sample one. Okay, so we go back. Yeah, so that's the this composition here for sample one, and then we have three more samples, sample 2, 3, and 4. And these three samples, you will not find it in any of the PVT reports like gas condensate or oil PVT report. Those samples are not there. These samples were created synthetically and introducing the different types of error that we have discussed. So sample 2, among these three samples, one of the samples has for example, an internal standard error. The other one has like only baseline shift error. The third one have both the internal standard and baseline shift error. But for like now, looking at these compositions, we don't know which sample has what problem. Okay, so these samples they were created just to illustrate the workflow that we are discussing here, and then you can use the same workflow once when you get new compositional data for your field, and if you have a very well robust gamma distribution model tuned to the and to the data that you have, like compositional data that you have from the field. Okay, so we start with this for this sample one. So we have like here four spreadsheets using the data for each sample. So in all the spreadsheets, everything is the same. It's just we are using the compositional data for the different samples. Okay, so we go to sample one spreadsheet. Okay, so now here there are a bunch of things. Some of them we have discussed already. So for example, here we have a shape factor. We know that for this, these are gamma model parameters, the shape and the bound. So this is the alpha value, this is eta we have discussed. So these numbers you should know, and those are well tuned. They cannot be arbitrary. Okay, and then these are upper bound molecular weights, or you can call the lower molecular weights for each carbon number here. We have defined in Excel when you're trying to use the gamma distribution model, then you need to define upper boundaries and not the lower boundaries, but it's the same thing. Lower boundaries can be the upper boundaries for the components. So the like for example, the lower boundary of C6 or like lower boundary of C7 is the upper boundary of C6, for example. So it's the same thing. And then you have reported average molecular weights. So these are the lab reported molecular weights of each component, and these are not so important for our calculations, and they are not going to affect the workflow that we are going to use. So even if you don't use them or you don't have them, it doesn't matter. Okay, so that's all about the data regarding the gamma distribution model. And now we come to this table here, which is which looks a bit complex. And yeah, so here in this table, what we have done is we have programmed the gamma distribution model. Okay, and then for example, this y function here or q function here, po function, p1 function, these are the different parameters that are used in the gamma, not the parameters, but like different terms or functions being used to to program the gamma distribution model, and these are given in these equations in the monograph, equation 5.22 and 5.20. And there I have a small comment that the equation in the monograph, it has some typo, so that's also mentioned here. So these are the different equations given in the monograph. And then Mi, that's the individual component molecular weights coming from the gamma distribution model. And that's something we generally discuss in the advanced PVT course when we discuss the gamma model in detail, that the gamma distribution model doesn't only give you the amounts of the different components, but also the component molecular weights. So these are the component molecular weights calculated from the gamma distribution model here. And then we have the calculated mass amounts. So mass amounts calculated, and why they are gray, because they don't sum to 1, and we will see why. We would like to have some normalized mass amounts. So these are the calculated mass amounts here, and then these are normalized mass amounts, meaning that they are summing to 1. Okay, so that's just taking this mass here divided by the total mass. So these are normalized mass amounts, again calculated from the gamma distribution model. And then we have for each component calculated mass. And now this is not the same as this one. This one is calculated mass, and also this one is not the same as this one. This is the calculated mass, taking this normalized mass and correcting it to the new total mass. Okay, so you see here in the comment, calculated mass corrected to new total mass. And that's something we discussed briefly before, that when we will be doing the exercise, we'll be calculating a new total mass using the gamma distribution model, and that's something we will see on the top of this spreadsheet. But this one is linked to this cell here, for example, and this new total mass that's calculated here. But we will come back to this section that's on the top here. So that's the calculated mass for each component corrected to the new total mass. So this, all these columns, all these numbers, they should sum to the new total mass that's there. Okay, and then these are the reported mass amounts, and also we are using normalized numbers here. And the reason why we are using normalized numbers is because the distribution model, the gamma distribution model, is just a probability density. It's a probability model. Okay, and we know that in the probability function, the sum of all probabilities should be equal to 1. So that's why we are using normalized numbers for the use of a gamma distribution model. And so there's normalized reported mass. So these are for C7 plus fractions, and that's something that was like the topic there. We will be when we introduced the topic, we said we will be doing the QC of CN plus distribution, the mass distribution of the flash oil. So that's why here we are doing the QC of the C7 plus data. Okay, but again, when we will finish the process, when we find out that what's the problem, the new mass, the new mass we calculate, or the corrected composition we calculate, it affects the entire composition, the mass fractions of all the components. Okay, depending on what type of error you have, and that's something we will see again in this exercise, hopefully. So here, this is just taking the data from this data sheet, and then dividing the mass of each component by the total mass, like the sum of the entire column. Okay, so that's, and that again, this should sum to 1. And then this is just the weight factors for each component, like what the amount, like which component are which component we believe is accurately measured, or which amount is which amount we believe is accurately measured during the gas chromatography. Okay, so again, this is linked to what X you choose here. Okay, and we will come back to that in just a short time. And then here we are just calculating the residual, so that's the sum of the this column, which is the total residual, or and then here is the total RMS. Okay, and the RMS that's calculated here, it's calculated in a strange way, because we are following the same process that FaceCom uses for RMS calculation. And when FaceCom calculates an RMS, or the residual, for when doing the gamma distribution model, it uses the reference value, because we know that when you calculate residuals, so you have calculated data. Okay, so when you calculate residuals, so you have a calculated data minus you have lab data, and then you have some kind of reference in the denominator. Okay, and for this purpose, for the gamma distribution model purpose, this DI reference, this is equal to 1. And one we know here is that it's the maximum value you can have for any component amount. And this is also a clever way of defining an RMS, because now if the reference value is 1, it means automatically, even if you have the same weight factors for all the components, the amounts which are big in magnitude, they will automatically be weighted more during the regression process. Okay, so their residual will be considered more important to be minimized, while when we will be minimizing the total RMS. So that's a clever way from Aaron to define the RMS root mean square for doing regression on the gamma distribution model parameters. Okay, and then these are just the molar amounts calculated. So these are lab reported molar amounts using the lab reported molecular weights, and the mass amounts of the lab reported data, and the average molecular weight. But again, these numbers that they are not relevant here for the calculation. We are using the mass amounts, and this residual is defined between the mass amounts, the calculated mass amounts, the corrected calculated mass amount, and the lab reported mass amount. Okay. Okay, now on this spreadsheet, we need to discuss what's here. Okay, so X, we have already discussed this. X is the first carbon number from which you think there is a problem in the chromatography, or like there error starts to happen from that carbon number. For example, if you have a baseline shift problem, and if you have only internal standard problem, then X would be the heaviest fraction, right? Because then you have only problem in the heaviest fraction amount. And okay, so then what we have here, yeah, we can discuss this first. Cx minus amount reported and Cx minus amount calculated. Okay, what do we mean by that? So we now know what is Cx. Whatever x you're gonna choose, that will be your Cx. So for example, if x is 26 here, then the Cx would be your C26, or like C26 plus. So this will be yours. This would be your Cx. And once you choose a number here, 26, what automatically happens in this spreadsheet, that component will be assigned a zero weight factor. Okay, and that's something we will be doing, because we know that's the component from which the problem starts, right? So if I, for example, choose 20 here, so what is going to happen now? Like all the components starting from 20 until the heaviest fraction, they are assigned zero weight factor, because now I know this is the first carbon number from which the problem starts, and it is going until the heaviest fraction. So we'll just keep it 26 for now. And so once now we have understood what is X. So Cx minus amount reported. So that's just the the sum of all the components that are sum of the amounts of all the components that are less than x, which are like until C25, for example. So if I just sum these numbers here, you see it's 0.7832. So 0.7832, that's the reported amounts, the reported total amounts for Cx minus component. Okay, and then same goes for the calculated data. So if we have, this is the calculated data that we are using. So if we sum all the amounts until the 25, again you see it's 0.7832. Okay, so and then Cx plus amount multiplier. So this is something that we changed during the regression. Because what we discussed before, that when we will be doing the gamma distribution model to match the relative areas, as part of the process, the gamma distribution model process, the process should also give us a new total calculated mass, right, which is here. Now to get the new total calculated mass, we have already written an expression here, which is here. MT calculated is sum of all the mass components until x minus 1, which is what we have mentioned here, Cx minus amount. So that's what we know, and then it should have a new calculated Cx plus amount. Okay, Mx plus calculated. So that's what we are trying to find out here. So this is Cx plus amount multiplier. So multiplier is like you have the lab reported amounts for all the Cx plus fractions. So here in this case only the heaviest fraction. So you have this guy here, and then you are multiplying this number here with this value, okay, to calculate a new value, a new mass of this component. If I had, for example, 20 here, then what this multiplier would represent is that all the components that are heavier than C20, like C21 plus, the total mass of the C21 plus will be modified with this number. It will just multiply the current mass of the C21 plus component with this multiplier and give you the new total mass. And so we just bring it back to C26. So the new total mass is just the sum of the lab reported Cx minus mass and the amount multiplier Cx plus multiplied with the Cx plus lab reported mass. Okay, and here what you see is that, like, here I have selected, for example, the entire column, but this is just the logic there that it automatically selects. So you see that this here, the formula in the new total mass, it's linked to a bunch of cells. So it's linked to this column here, it's linked to this column here, but this is just to make the sheet very generic, so that whenever you select, for example, an x value, everything is adjusted accordingly. So what this formula is doing, it's trying to find out, okay, it's trying to compare this value x with this column here, and then see whenever you get a number that's equal to or greater than this number here that you have input, and wherever that happens, what it does, that it sum the component amounts and it multiplies it with this amount multiplier that it has calculated as part of regression. Okay, so what we discussed during the presentation, that for each sample, since we don't know what is the error type in the chromatography, so what we will be doing is that we will be using a certain workflow, and we will see how it works. But to use the workflow, what we need to have is we need to gather some data. Okay, we need to calculate some data, and to calculate that data, what we should be doing is that we should be changing this x value, for example, for starting from 16. Okay, starting from 16, and then we go to, for example, in the data, we go to solver. Okay, and here the solver is already set up, so we'll try to minimize this RMS. We have two variables to change: the average molecular weight, that's your C7 plus molecular weight, that's what something we discussed, right? That the this molecular weight will be regressing on the C7 plus molecular weight. That's one parameter in the gamma distribution model that will be different from one sample to another. So that something we should be regressing on while matching the gamma model. And the other is this amount multiplier that we want to calculate. And then the constraint is that I3 equals to I4. Yeah, so that's an important part here that requires some attention. And what this means is that the Cx minus amount reported and the calculated value has to be exactly the same. And why that's the reason why that should be the case is because we know that uh, what we are trying, like when we were discussing the different types of error, we discussed, okay, we will be matching the relative areas, right? And so the relative areas, for example, calculated versus ARI lab value. Now the when if we define a residual as, for example, ARI, like if we define a residual based on these two numbers here, calculated and lab value, okay. So here we know that the relative areas, they are just the area of each component divided by the sum of all areas until x minus 1. Okay, so we can also say, for example, we can just write it like ARI calculated minus ARI lab. Okay, and then we know the reference is 1, so that doesn't matter. But then we can also write it like okay minus a so that's not then that should just be I lab value. Okay, so that should be lab and that should be calculated. Okay, so you can write a residual like this. Okay, but the way we are define like the way we are defining the residual in this spreadsheet is that we are using the individual component mass or the areas, and we are just calculating the difference between these two. Okay, so what we are doing is we are just calculating the difference between this guy and this guy. But and that's one other way of defining the residual. But in that case, if we define a residual by just the difference of these two, what we should be doing is that we should constrain our regression problem such that these two are exactly identical. Okay, so meaning that you have a common denominator. Okay, so you have a common denominator, and this common denominator, it should be equal to the lab data, like the calculated values, the sum of the calculated values should be equal to the lab reported values, because we believe that those areas that the lab has measured for all x minus component, those should be accurate. Okay, so the sum of all those areas should be accurate, and then we are trying to conserve that. If you only define a residual, yeah, if you only define residual like this here, and we don't constrain the total area, like in our regression problem, then what could have happened that uh, the sum of these areas, the calculated areas and the lab reported areas for all x minus components, they may not be exactly equal. Okay, and that's not a good thing, because what we believe strongly that those areas are accurately measured, and we should conserve that total area that we think is accurately measured. So that's what we are trying to do here. Okay, so residual is defined based on these two numbers here, the difference between these two values, the mass or the areas of the calculated and the lab, and we are conserving the total area for all x minus components. Okay, so I guess this was hopefully clear what is being done in this Excel spreadsheet. So yeah, so we were trying to use the solver starting from x starting from 16, and then we say okay, solve, we press the solve button, and then it's some minimization, and then you see it has calculated an RMS value, so which is kind of close to, for example, 0, and then that's something I have already done, for example, and I have compiled the data. But what we should be doing is that for each x, so for each x value, uh, we can do it like, for example, x value, we can do it here. So for each x value, you need to note down the RMS, okay, and you also need to note down the MT calculated value, the new total mass. So for 16, we have 0.028 RMS, and then the calculated mass is here 1.0107. Okay, and then we go to 17, for example. So we say 17. Okay, so RMS is also about the same and very close to 0, 0.029. Calculated mass is 1.0073, close to 1. And this you need to just continue the process until you go to, for example, the last fraction, which is 26. So data solver, okay, so still like until 26 we have very close RMS very close to 0, and the calculated mass is also close to 1. Okay, so you just need to compile this data, and then you need to plot the data as shown in this presentation here, okay, on the left. So that's the plot that I was talking about. There is also this gamma shape, and that's not an important property that we will be looking at. We are only interested in the total calculated amount, this number, and the RMS value. Okay, and for this sample one, if you will do this exercise, and I did the exercise and I have plotted the data here. If you look at the plot, what you will find out, okay, for starting from C16 until C26 plus, if you only look at the RMS, so this is the RMS points, this, and you see all the RMS values, they are kind of close to 0, okay. So every time you choose a new x value, you always get almost perfect fit of the data, okay, and perfect fit of the data for which the residuals or the weight factors are 1 or non-zero, okay, And when you remember that when we choose the last fraction, which is 26, the weight factor on the last fraction is also zero, right? And all the rest are 1. So the amount of the last fraction is not being used in the regression, is not being considered during the minimization problem. Okay, so what we see here that at all x values, the RMS is 0. And this, only looking at the RMS, this is gonna give you what is the correct x value. Okay, remember, like when we discussed these baseline shift and internal standard problems, we discussed like if you have baseline shift problem, the x value is somewhere, it starts somewhere like between 15 to 25. And if x value is only 26, or if x is just the last fraction, then most likely you have an internal standard error. So if you only look at the RMS here, okay, this is gonna give you what is your Cx value, because the way we define Cx is from this plot. If you want to choose a Cx value, so it is uh, the last component that you can find with an RMS, with an RMS that's minimum or close to 0. So here we have, so again, Cx is the last component on this list. So if you start looking at here, so just look for the last component where you have where the RMS is either minimum or it's close to 0. And here we see that the RMS at all points are close to 0. So what's the last component here? That's C26 plus. So the Cx here is C26. Okay, so that's the first thing that we have figured out. Okay, now we will utilize the data from the total calculated mass. And if you look at the total calculated mass, what have we found out that and since after we have determined the Cx value, we will look at the total calculated mass at that Cx value. Okay, so this is our now Cx. So we go out on this component and see what is the calculated total mass for this Cx, and that's this guy here. And if you see that this number is very close to 1, okay, 0.99 or 1.0, so the MT calculated is equal to 1, okay, from this plot for this particular sample at this Cx value. So this is at Cx. Okay, so when we have these two information, we can magically tell uh, what kind of problem uh, we have in this gas chromatography data. Okay, so when we have Cx is equal to C26 plus, this is suggesting that we may have an internal standard problem only. Okay, but just knowing the Cx value, you cannot guarantee, okay, you have an internal standard problem or not. So then you go to this total calculated mass from the gamma model, and if it's close to 1, it means that there is no problem in the gas chromatography data, because we know if we look at this Excel spreadsheet here, okay, we have 26. Yeah, and if you have this Excel spreadsheet here, these are the normalized lab reported mass amounts, and the sum of these mass is equal to 1. Okay, so it means the lab reported total mass is 1. So if the calculated mass is also 1, this is gonna suggest that there is no uncertainty or there is no error in the total mass. And we know that the error in the total mass comes from the internal standard. Okay, so this is also equal to the lab value, which is suggesting that there is no internal standard error. Okay, so Cx suggests that there may be an internal standard error here, but then when we look at the MT calculated value, this is suggesting that there is no internal standard error. And if you make a plot of the calculated mass amounts versus the lab mass amount. So here you see we are plotting the mass amounts versus calculated molecular weights. You can also use reported molecular weights, whatever you want. But here we are looking at the mismatch between the reported and the calculated masses. And you see that you have a perfect fit of the gamma model is giving you a perfect fit of the lab data. Okay, and this is suggesting that there is no measurement error. There is no gas chromatography measurement error. It's a perfect composition. Okay, so now hopefully with this first problem, it may be clear what's the workflow and how we utilize the knowledge. So now we go to our next problem or the next sample, which is sample 2. Okay, and if we do the same exercise, so that's here. So that's being done here, and so a sample 1 sheet and sample 2 sheet are exactly identical. The only thing that's changed is these numbers here, which are linked to now column C. In the previous sheet, they were linked to column B. Okay, so we have the data for sample 2 in column C. Okay, so again, to identify the problem, we do the same exercise here. And when we do the exercise, plot the numbers, RMS and total calculated amounts. So now we need to find out first what is the CX value. Okay, again, the definition of CX, we can just write it here so we remember. CX, last component on the plot with minimum or 0 RMS. Okay, so that's the component we are looking for. So if you look at the RMS data here, these are RMS values. Okay, and you see all the RMS are like close to 1, so that again the CX would be 26 plus. So you can just write it here. CX is equal to C26 plus. And when we have CX is equal to C26 plus, this is immediately tell us, okay, there might be an internal standard problem. Then we go and check the total calculated mass at this CX value. So MT calculated at C26 plus is equal to so if you go to the total calculated mass, which is this guy here and this guy here, and you see it's not even close to, yeah, it's far removed from the one values. It's about 0.8 or something, so 0.80. Okay, which is not equal to one value, not equal to, which is actually the lab reported total mass. Okay, so now this is confirming that this sample has an internal standard error. Okay, because we know that the total calculated mass has to be the same as the lab reported mass if you don't have internal standard error, but here that's not the case. And this was suggesting that there might be internal standard error, and this is confirming that there is an internal standard error. And when we compare the mass amounts, the reported and calculated values, what you see from the gamma model fit of the data, that you are fitting all the data perfectly except for this last fraction. And this guy, we know that if you have an internal standard error, that is going to give you a wrong total mass or total area, and that's going to affect the amount of the heaviest fraction. Okay, so again, just write that down. The equation that we have seen before is the total mass or total area, which is uncertain here, minus sum of all areas or mass fractions, whatever you want to call it. Okay, So that's what we are seeing here. The this is reflect the error in the total mass is reflected only in the error in the heaviest fraction here. And uh, yeah, so when we looked at the samples, we like just looking at the sample composition, the three sample or like four samples, we don't know which one is a perfect GC data, which one has internal standard problem, but this workflow is kind of telling you which sample has what problem. Okay, and if we go to the next the next sample, which is sample 3, again we do the same exercise, plotting uh, the CX versus the total calculated mass, and also the RMS is here. And again, first we need to find out what is the CX value. Okay, so here what's the CX value is, we can see the CX value is C20. Okay, this guy here, because if you look at the RMS, here you have the minimum RMS, which is also close to 0, and then you start increasing the RMS. Okay, so this is our guy. So CX is equal to C20. Okay, and then we are looking for the total mass. So and this guy here, so the total mass is 1. Okay, which is equal to the lab reported total mass. Okay, so what what this is telling you, when we have a CX is equal to C20, this immediately tells us, okay, there might be a not it's not there might be there is a baseline shift problem. Okay, and once we have determined, okay, there is a baseline shift problem, we're just looking. But in the previous one, when we have the CX is equal to C26 plus, we were not that's not gonna tell us whether there is an internal standard problem or not. Okay, what you can just say by just looking at CX value, if it's the heaviest fraction, that there might be internal standard problem, and then the total calculated mass gives you the confirmation whether there is internal standard problem or not. Here, when you have a CX value which is less than the heaviest fraction, for example, if it's 25 or 20 or whatever value, this is immediately going to tell you there is baseline shift problem. Okay, so this immediately tells about existence of BS problem. Okay, so this CX value is immediately telling you about this. Now when we look at this, when you know, okay, there's baseline shift problem, the second question comes in mind, whether there is only baseline shift problem or is there an internal standard also. Okay, so then what we do is we see what is the total calculated mass, and if the total calculated mass is the same as the lab mass, which is the case here, then this will tell you no internal standard problem. Okay, so this is going to tell you that there is no internal standard problem, because we again the total calculated mass, any error there is introduced by the internal standard alone. So there is no internal standard in that case. And here if you look at the plot, what you will see that the gamma distribution model is giving you almost perfect match until a certain component, and then you start deviating uh, from the lab reported data. Okay, and then you also have a mismatch in the heaviest fraction. But here the mismatch in the heaviest fraction is not because of the internal standard, but it's because of the baseline shift problem. And that's something we also discussed before. Again, we can just write it down that the amount of the heaviest fraction is not just a function of the total mass or the total area, but also the mass of all the components. Okay, and we can break this into two sums, so x minus 1 and also starting from x to n minus 1. Okay, so here this uncertainty is coming from these numbers here, which are uh, due to ds. Okay, so this guy here is accurate, the total mass or the total area, and these are also accurately predicted by the gamma model, but due to these errors here, you have a mismatch in the heaviest fraction. Yeah. So that was our third sample, and then we have a fourth sample, and as you might have already guessed that this sample has both problems. But again, let's say we don't know about it, and we try to see from this plot here, this identification plot. So what you again see that we have C20 here. So that's our C20, that's our CX. So CX is equal to C20, and MT at Cx is equal to go here, that's about 0.95, which is not equal to MT lab value. Okay, which should be 1. So now this tells us that there is BS problem, and this is telling us that there is also IS problem. Okay, there is also an internal standard problem. And if you look at this plot here, yeah, so here when you look at this plot here, then what you can see is that you have a mismatch here, you also have a mismatch here. This plot looks very similar to what we had before in the baseline shift. So just looking at this plot, you cannot say whether there is a baseline shift problem or internal standard problem, or whether there is only baseline shift problem or there is baseline shift and internal standard both problems. So that's why this exercise that we are doing here on the left, we need to do that exercise to pinpoint what is actually the problem in this in the given compositional data. Okay, and here the amount of the mismatch in the amount of the heaviest fraction is not just because of the baseline shift problem here, the mismatch in these areas, but also the mismatch in the total area. So in the here, when we wrote this equation here, so here we introduced the error in this guy here, and this caused an error here. But now in this fourth sample, we also have an error due to this total area. Okay, so that's how we identify the problem. Okay, and what this error identification problem process is giving us, it's giving us information on what kind of error is there in the gas chromatography data, and also it is giving us the information about uh, from which component the problem actually starts. Okay, and so, as I mentioned earlier, that these sample 2, 3, and 4, those were synthetically created, and when we created those samples, we introduced those errors exactly starting from these components. So this method is exactly pointing out the right component from which we actually started introducing the error. Okay, so without knowing, without the information that I just mentioned to you, you can actually use this workflow and find out what is exactly the problem in the gas chromatography and from which component it starts. And this all looks quite a bit simple, but I need to emphasize one more thing here. First thing, I need to emphasize on few things. One, you need to have a well-tuned gamma distribution model. And what do we mean by well-tuned gamma distribution model is that if you have a perfect GC data from your field that you are looking at, then the gamma distribution model should be able to give you a perfect representation of that accurately measured GC data. Okay, so that's the basic assumption behind all this workflow. And once you have that, uh, here, like when we are looking at these signatures, these are like, you can say like book examples, okay? Simple problems. But when you will look at, for example, the real GC data, these plots that we are making here for the error identification, they may look a bit messy. And there comes the experience, okay? Like we have worked with a lot of problems. We have looked at a lot of GC data. Have gone through this process on a lot of different examples. So we kind of know how you can exactly point out the error there. But yeah, so that's just a quick point here that we are looking at simple examples, like synthetic examples where these errors can be very clearly identified. But if you have data from real field and if the data looks quite messy, then these plots may also look quite messy, and then there comes this experience factor. But nevertheless, you can use this workflow if you have the well-tuned gamma distribution model. Try to find the error in the measured GC data. Okay, so just yeah, we are almost finishing this topic, but I just want to mention quickly, like summarize. Yeah, so not here, but just adding one page, and then what information we are getting from this error identification process, or this the workflow that we are using. One, what kind of GC error is present? So that's one information that we are getting. And the second information we are getting is what components are affected by the measurement error. Okay, so that's something we have already seen. What we can identify what kind of error is that and what are the components affected by the error, which is the CX value. Okay, now the third question is um, okay, so the third question is, okay, we have found the error, we have found where the error actually is. Can we find a corrected composition? Can we correct those compositions um, once we have found the errors? And that's something we can try. in this exercise here. So, okay. So the question is, can we find the corrected composition? So in first, the correct CX value is this. So we have the solver, I guess. Okay, and then we have also here, we know that the correct CX value was 26. So now what we are doing first, we are just adding the correct CX value for each sample that we had it on this workflow, and then just using the solver to find the solution here, and then we'll see how we can use the solution to come up with the corrected composition. Okay, so this was the baseline shift problem. The x value was 20, and you see that for this x value, the total calculated mass is about 1, which is giving the information that there is only baseline shift problem. Okay, so this is also solved. So now on this sheet, what we will try to do at least, is to calculate the corrected compositions. Okay, so we have components which are here at least, yeah. So just drag them down. Just link these cells with that sheet. Okay. Now we have sample 1. Okay. So okay, so for sample 1, we found out that there was no GC error. So it means that if we um, so there was no GC error, means the total calculated mass and the lab reported mass was about the same. So we can calculate what we can say that the same composition, we can use the same composition because there was no error. So the corrected composition is the same as the original composition. But just to just to calculate the correct just to show you how we can calculate the corrected composition, is that if we take this composition here, okay, because when we did the gamma distribution modeling, we did it for C7 plus fraction, okay, and for all the fractions that are less than C7, those are kind of given in the lab, but we know that the total mass might have changed. Okay, so we need to, if we are calculating the mass fractions, then this should be linked to the new total mass, which is here, should be about the same as 1. And okay, so that's something we can drag down onto C6, and then we have a C7 calculated value, which is here divided by this number here, and then this has to be, sum has to be Okay. So yeah, I think we can do it in two steps. So first we will have sample one, we have mass. Okay, so the mass, we know that the if you look at the lab data here, okay, these are the mass amounts for all C6 components, and then we have for C7 plus we calculated a new total mass, so which is this guy here, and these are the individual component masses. Okay, so we link this one, and then we just need to, yeah, so this will be the new mass of, for example, for C7, then we just drag it down, and then we calculate what is the total mass, which should be the same as the mass of where is the, yeah, auto sum here. Okay, so that's the total mass, and then we can calculate the weight percent. Okay, which will be this divided by this number here. Oh, oh man, no. Okay, so forget about this. Yeah. So when we did this exercise, we calculate a new total mass of the C7 plus fraction. Okay, so it went from 1 to 0.9916. It means that whatever C7 plus we had from in the PVT lab, whether it was 20 mole percent or 20 mass percent or like 50 mass percent, that should be multiplied with this value. Okay, so what we need to do here is that we can calculate the C7 plus values from the lab data for each of these. C7 plus mass, okay, which is the sum of these numbers here. Okay, so for each sample we have calculated what is the lab reported C7 plus mass, and now when we are correcting the composition, so this first we can calculate the mass, and the C7, the mass of C7 would be, we go here, no, not here, sorry, we go to the sample sheet where we have the calculated mass. Okay, and then we just because these are normalized, right, we normalize it to the total. And we are doing the gamma distribution model, everything is normalized to the total mass that was reported by the lab. So we just multiply this with the lab value here. Okay, and then we just drag it down. Oh, sorry, we have to this one, but this needs to be fixed. And so we drag it down, and then we calculate a total mass here, which will not be where is the sum? Yeah, so see that there it's not exactly 1, because there we have, when we calculate the total mass here, there it was slightly different. So then here we can calculate the mass fraction. maybe in percentage it would be better. So just multiply by 100, and then yeah, and then this is mass percent. Okay, and this composition that we have calculated here, it should be similar to what we have, should be very similar to what we have from the lab data, because we know that there was no problem in the chromatography, right? So like for example, if you look at C2 0.14, C2 0.14, if you look at the heaviest fraction 19.46, and the highest fraction, it's slightly different because the calculated mass here is not exactly one, of course, because you can have like the distribution model here, it's not like pinpoint matching every component. Okay, so you have slight differences here. And you can also see it from actually here, like this, we are matching these two together, calculated versus the lab data, and then you see here that there is a small mismatch between the different components. Okay, 781 to 779, but the RMS is close to zero. Like it's a very good match, but not you cannot force the model to exactly match each component accurately, right? Pinpoint matching with a pinpoint accuracy, and you have also some mismatch in the heaviest fraction. So okay, so that was the so, but what we can see that this composition that we are getting here, it's very close to what we have in the lab from the lab data. So when it's a perfect composition. Now we go to sample 2. Okay, so for sample 2, again, what we're gonna do first, we calculate the mass, and then for C6 minus, we know that those mass are the same as the lab data, and then for C7 plus, we have new calculated mass. This number multiplied by this number should be fixed. Okay, and then we have what was something is not right. Sample 2. Okay. This should be multiplied with this guy here. Okay. Yeah. So now then we just need to normalize it with respect to the total mass, calculating the mass percentage. Also, okay, so that's we can just format it. Oh, what are we doing here? So this has to be exactly the same, and then for C7 plus, the amount should be, we have the we have this sample 2, the calculated mass, okay, multiplied by, go to the data sheet and then use this mass here, and then just drag it down. Yeah, okay, so that's again, yeah, this thing, and then we can also calculate the corrected composition um, for sample 3, and then yeah, and then maybe you can do for the fourth one by yourself, but we just do it for sample 3, and then I'm going to show you something uh, like how good is this method is for correcting compositions. So again, for sample 3, go to this sheet here, take the amount for until C6, and for C7 plus, go to the sample 3 sheet, get the calculated mass multiplied by the total C7 plus mass we have, and then fixing it, and then drag it down, and then just renormalizing it to the total mass. Just formatting it a bit, and then okay, let's see what did we do wrong here. The C7 sample 3 L14 L14 times D36. Oh, what the hell happened? Oh, okay. So um, Yeah, so we did this corrected composition calculation for the three samples. And so one thing that I can mention it to you now, since we have finished the exercise, and now we're gonna just quickly check how good is this method for uh, how good is this method for correcting the composition. Is that when we look at the data that we actually have used for these calculation, what I mentioned it to you, that this first sample, that's from our PVT report, right? The gas condensate PVT report. And these three samples, they were synthetically created, and each of them had a different type of error, baseline shift, internal standard, and the third one had both errors. And those errors that we created synthetically for the illustration purposes. But when we created those errors, the base composition that we used to introduce those errors was actually this composition, this from sample one. Okay, so sample one composition was used as a base composition to introduce the errors, because this is like a perfect composition. You see it almost perfectly falling on the gamma distribution model. So we introduced the errors in this composition to get these three other samples. Now, when we are doing this correction to these compositions, with the like we know that these compositions are with errors, and when we are calculating the corrected composition, what we would expect is that the corrected composition should be very similar to sample one. Okay, because that was the composition we used to introduce the error. So the composition that we should get at the end of this process of correcting the composition, it should be very similar to this sample one. And that's something we can compare quickly here. That for example, sample one, these are the mass amounts calculated, and these are the mass amounts for sample two that are calculated. These are the mass amounts for sample three calculated, and you can also have here the known composition in weight percent, which is this sample one actually. Okay, and then we can just calculate the error. For example, sample one error percentage, meaning error means that how different is the corrected composition with respect to the known composition. So just error should be the calculated composition minus the known composition divided by, for example, the known composition, and then we just can multiply it by 100 so that it's an error. We just drag it down for all components. Yeah. Okay, so these are the errors, like 0.7%, 7%, 0%, which is like in terms of percentage, these errors are almost nothing. We can just also maybe in terms of the percentage, because percentage doesn't reflect really what the error is, how much the error is actually, because you can have very small amounts and very small differences, and the percentage can go crazy. So we can just calculate the difference, which is calculated minus the known composition, and you see like it's 0.01, 0.03. It's only in the heaviest fraction. There is some, but it's a very small amount. Okay, so that's kind of telling you how good is the method in correcting the compositions. Uh, if you have a well-tuned gamma distribution model, and if you have followed the workflow correctly. So we can also do the same for this guy here, but here we can just make sure that we fix the reference. Okay. So again, you see it's about the same magnitude. And then sample 3. Yeah, so about the same. So this was a good exercise, I guess, for to uh, to give you an idea, like with this workflow, it's not just matter of finding what's the problem, but also correcting the problem so that you can use the corrected composition for your calculations. And with this, we can also say, where is my pen? Hmm, yeah, here. Yeah. So with this, we can what we can conclude is that you can find and what kind of error is there in the GC, and oh, you can also find which components from which component the error starts, and also you can find the corrected composition. Okay, very accurately. So with this, we finish this topic on compositions QC. Hopefully, it was not bit confusing, and hopefully you guys have learned from it. And yeah, very good.